we've kind of seen if the group delay is constant, we know how to interpret that. If the group delay is constant, it basically says at any frequency you're going to get a delay of the group delay. So the next issue has to do with how to interpret group delay more precisely when the group delay is not constant. There are two kind of steps to doing that. One step to doing it is to just focus on a narrowband signal. What you'd kind of like to say perhaps is that, well, if it's a narrowband signal, then what's going to happen is that that signal is going to just be delayed by what the group delay is. That's not quite right. It gets a little more precise than that. And the procedure for the analysis is straightforward, although when you look at the math, it just looks like math. So what I'm very eager to encourage you to do is not write a lot of equations. Don't write any equations. All the equations will be on the slides, and focus on what the equations are saying. That's what's important. And then at your leisure, you can kind of work out the math more precisely. But here's the basic idea. I'm talking about a signal that's narrowband, and talking about the phase characteristic being nonlinear. So the phase is different at different frequencies, the slope is different at different frequencies, but I'm going to first just focus on the narrowband signal. If the signal is narrowband, then around that frequency, suppose that I approximated the phase curve with a Taylor series expansion. So there's the 0th order term, which is just going to be what the value is, and then the 1st order term, which would capture the slope of the phase curve. I think you would easily agree that if I have a narrowband signal, and this is what the Taylor series expansion is around omega 0, that from the point of view of the signal and the output, you would not be able to distinguish between this system and this system. In other words, I can replace this phase at that frequency by just the Taylor series expansion. So that's the basic idea. Now, if I say I'm going to replace the phase at plus omega 0 and minus omega 0 by the Taylor series, then I can look at this as the cascade of two systems. So one system just is this offset, which is to account for the fact that this intersects the axis at plus phi 0 and minus phi 0, not at 0. And then cascading that with a phase curve that simply has a slope that's minus the negative of the group delay at that frequency. So this is just simply describing this in two pieces, because if I have two systems in cascade, the phase of the cascade is the sum of the phases of the two systems. Phases add when you multiply, obviously. Okay, so let's first, and this picture is in continuous time. Exactly the same picture would apply, or the corresponding picture would apply in discrete time. So what does this system do to this input? Well, it's an input that, and I'm assuming this is an all-pass system, so let's just have a magnitude equal to 1, and then this is the phase, or an amplitude equal to 1, and this is the phase. So this output is just the delay of this input delayed by the group delay. And the reason I kind of have this picture in continuous time rather than discrete time is because that lets me avoid for now the issue of, well, if that slope is a non-integer, what does that mean that it's delayed, and that sort of thing, and we're going to deal with that. But that's not the point at this point. It's pretty obvious what this system does. Now, the question is, what does this system do? And what that system does is pretty simple and straightforward, because what we have is we have x of n, and I'm going to do this in discrete time. X of n is s of n cosine omega 0 n. And more generally, we put it up there in terms of putting a phase factor in of theta. Let me just kind of write this out for now without the phase factor because it's just, there's less clutter in the equation, but on the slide it has the phase factor. So, and S of n is narrow band, and so we have a spectrum then. So this is S of n, and there's a half, e to the j omega 0 n plus e to the minus j omega 0 n. So that's what I'm putting in, and here's the piece around omega 0 and the spectrum around minus omega 0. So what does this do to this signal? Well, it's pretty easy. It takes this one and multiplies it by e to the minus j omega 0. Or is it e to the minus j omega, I'm sorry, e to the minus phi 0. Or is it e to the minus phi 0 n? No, it's just e to the minus j phi 0. So, and this one gets multiplied by e to the plus j phi 0. So what I'm going to get out, just due to that, is I'm going to get out y of n, which is going to be S of n and a half. And then this one is going to get multiplied by e to the j minus phi 0. And I'll have e to the j omega 0 n. And then I'll have plus e to the plus j phi 0, e to the minus j omega 0 n. In other words, this is going to be a half cosine omega 0 n minus phi 0. So what I'll get is x of n will generate as an output S of n times cosine omega 0 n minus phi 0. That's all. And I can actually write that a little differently, which is sometimes convenient and will be. I can write that as cosine omega 0 n minus phi 0 divided by omega 0. And in that way of writing it, I can interpret that actually as a delay. And that kind of delay ends up being referred to as a phase delay. It's a delay that is associated with the phase. Okay, so it's important that you understand that this is not hard to deal with for a narrowband signal. For a wideband signal, it's a little trickier, but because of this discontinuity. But it's important to understand that for a narrowband signal, it's pretty straightforward. Okay, so here's the math. Let's just quickly bounce off the highlights of the math. This is our x of n. I now put this phase factor back in. So what comes out of the first system being just the one with this phase factor, is a phase shift of phi 0. Now I go through the second system. The second system, again, we're assuming the amplitude is constant. This has a group delay, which is the negative of the slope of the phase. And so what that's going to do is just take the output and delay it. So what we'll have is we'll have an output which is taking this output and delaying it by the group delay. Now I did something here that absolutely you should never do, and if you do it on an exam, I don't know what I'll do. Well, I do know what I'll do in terms of the exam, but I will be disappointed. So these quotes are because we're going to have an interpretation of what group delay means, even when the group delay is a non-integer. We're going to have an interpretation. And so sometimes when I'm talking in lecture or talking to you and I'll say, and this gets delayed by 0.7, you know what I mean. That's what I mean by the quotes. You know what I mean. Now, on an exam, if we're asking you about the output due to a non-integer group delay, I don't want you to assume that I know what you mean. But the interpretation will become much more precise pretty shortly. But for now, allow me to use the quotes so that we don't have to burrow into what this means when this is non-integer. And so the result is that I simply take this and delay it by the group delay. So that's just replacing n by n minus the group delay, and so this is what I'll end up with. And actually, if you looked at this factor is just what the phase is in that nonlinear phase curve, what the phase would be at omega 0. It's the combination of the constant offset plus the slope added into it. So this is what the result is. The interpretation then, when you look at this, is that for the narrowband signal, there are two effects. One effect is on the envelope of the signal. Remember, we're talking about a narrowband signal. The envelope of the signal, if you think of this as, let's say, an AM signal, the envelope is delayed by the group delay. You know what I mean. The phase is shifted by a combination of course, it started out with the phase of theta. That theta is now changed by a combination of the group delay times omega 0 and this phase factor times omega 0. Or you can think of it as a delay, just as I used the delay here. And that's often referred to as the phase delay. So any of you who kind of have a physics background or have come across what's referred to as phase velocity and group velocity and the difference between those, that's exactly the kind of thing we're talking about here. In fact, the analysis for that is exactly the same. Okay, so this tells us what happens if the signal is a narrowband signal. Next question is, what happens if it's a wideband signal? Well, because of the linearity of the Fourier transform, if I have a wideband signal, I can think of it as just a linear combination of narrowband signals, right? I mean, I can, here's my wideband signal, the Fourier transform of it, and I could imagine, for example, think of a bank of bandpass filters. And I put my signal into this bank of bandpass filters, and let's assume that those filters are such, and we'll be using this terminology toward the end of the semester, a perfect reconstruction filter bank. In other words, I take all those outputs, I add them up, and that's going to be equal to the original input. In other words, input to output, that system is an identity system. It's just that I've broken my signal up into multiple very narrowband pieces. That's what I'm saying here. I'm saying that any wideband signal is a superposition of narrowband signals. And so if I take a wideband signal and I put it through a system that has nonlinear phase, or equivalently non-constant group delay, it just means that each of these narrowband groups, frequency groups, is going to experience, the envelope is going to experience a different delay. The carrier is going to also experience a different delay, which is the phase delay. So that's what's going to happen. For example, here's a system in which this is an all-pass system. Here's the phase. This is the wrapped phase. This is the unwrapped phase. This is the group delay. If I put an impulse into the system, the Fourier transform is an impulse, is a constant at all frequencies. But what's going to happen if I think of that constant frequency content as being broken up into little narrowband pieces or narrowband frequency groups, each of those frequency groups is going to go through, the envelope of it is going to go through a different delay. So here's the group delay of my filter. And it suggests that frequencies around here, around here, around here, around here are going to essentially not have any delay. Whereas this frequency group is going to go through a fairly large delay as compared with this frequency group, as compared with this frequency group. So what I would expect to see in the impulse response is I would expect to see the high frequencies coming out first. And then after those, I'm going to see a frequency group show up with this delay, and then I'm going to see a frequency group show up with this delay. I said it's an all-pass system. You would think that an all-pass system, if I put an impulse into it, an impulse is going to come out. I mean, it passes everything. The thing is, an all-pass system passes all frequencies with the same amplitude. It doesn't pass all frequencies with the same phase. And so what you get is this effect. And in fact, in a communication channel, this effect is very important. In lots of contexts, it's very important, and it has a word attached to it. And now I am going to break my basic rule and say, how many of you know what that word is? Okay, let me give you a clue. It starts with a D. Dispersion? Dispersion, exactly. So what's happening is I start with an impulse, and all the frequency groups are added up in phase. So you look at that impulse, you got, boom, an impulse. You put it through an all-pass channel that has nonlinear phase, and what happens is that that impulse response gets dispersed in time with different frequencies coming out at different times. And so, for example, if you take speech and you play it through an all-pass system that has a lot of dispersion, it's going to be very hard to understand. If it has enough dispersion, it's going to be very hard to understand what's being said, even though the magnitude of the Fourier transform hasn't been impacted at all. Okay, so these are all very important things to understand, not just in the context of this course, although these issues will be coming up as we go along, but also just in general, developing your sophistication in terms of how to think about the effect of the phase of a filter, its effect on a signal.